Hello, welcome to the third lecture in ML series. Once we have defined a learning problem, how do we build a machine learning solution? In this lecture, we will be discussing what are the crucial design choices that go into designing a learning system. Let us quickly recap what we discussed in the last lecture. We have defined a problem as a well-defined or a well-posed learning problem. Any well-posed learning problem has three components: the task, performance measure, and an experience. The task can be a classification task or a regression task or a clustering task. Performance measure is a quantitative measure which tells you how well the machine is performing, and experience is the data that is used to learn. Now, once after defining this well-posed learning problem, next we have to build a solution. Now, to build a solution, what are all the design choices that we have to take? So, there are four design choices that we are going to consider. So, first one is starting from choosing a training experience. Is it learning from all the data once, or continuously adapting a new information when it arrives? Once after choosing a training experience, we have to choose a target function. That is, we have to formally define what the system is expected to learn, which could be an unknown function maps the input to output. Once after formally defining a target function, we have to choose a representation for the target function. The target function can be a linear, that means a linear representation between input and output, or it could be a complex relation. Once after choosing a representation for a target function, we have to use some learning algorithm that finds the best version of the representation for the data. Now we will discuss in detail these four choices. The first one is the choosing a training experience. The training experience can be a direct, like we had given a input-output pairs, which is common in supervised learning, or it could be an indirect, where you will get a feedback based on actions. In a chess game, something like because of this move I won, or because of this move I lost. It's an indirect feedback that you get after the result of that game. So, which is commonly used in the reinforcement learning. One more thing is whether we have all the data is available at once. Are we going to use all the data once for learning? That comes under batch. If we have to continuously adapt as the new information arrives, then it is online. In case of online, model has to learn continuously. An example, like if you take a response of a ChatGPT, after that response, you have an option of like or a dislike. Based on your response, it will learn. So that is the online learning. And next choice is choosing this target function. This target function is an unknown function that maps the input to output. If you take an example of a spam filter, the spam filter, what is expected to do? It should take an email, and it should say it as a spam or not a spam. In case of house price prediction, the attributes or features related to the house, like the size, the location, and price. So, and so, so what is the objective of learning? The objective of learning is to find a hypothesis that best approximates this unknown target function, that is close to this unknown target function. Here we are using a term like a hypothesis. Hypothesis is generally used to say when you want to assume something and then later you can change it. So we are simply guessing something or assuming something, and then we will refine based on whether it is giving a correct or not. That is the reason we are using a term hypothesis here. So once after choosing a target function, we need to choose a representation of this target function. There are some common representations like a linear function or set of if-then rules. In case of if-then rules, if some condition on input, then take this decision or predict something. Those kind of set of if-then rules you might have for a representation. Or you might have a decision tree, which is a flowchart like a representation, where you have some condition on attribute. Consider an example to understand this decision tree representation. This is a decision tree representation of the AND function, Boolean AND function. So you have two attributes A and B. AND function is true only when both A and B are true. So first you have a condition on A, whether it is true or false. So you have two choices, true or false. That's why we have two branches on that node. And when A is false, you know irrespective of B, it will be false. That condition here. And when A is true, again we have a condition on B. When it is true, you get true. When it is false, you get false. So this is a typical representation of the decision tree. And one of the beauty of this representation is it is interpretable. Like clearly one can explain why the machine has taken this decision. If suppose the machine is giving true, you can clearly say that both A and B are true. Like any decision tree, for any problem, if a particular decision is taken, you can clearly say that this condition on attribute, this condition on attribute, this condition on attribute, because of that it has taken this decision. So for learning complex patterns, we will be using artificial neural networks. So as we know, whatever the choice of the representation that we take, it is going to impact the learning power and interpretability. The linear functions, decision trees, and set of if-then rules, those are interpretable. But an artificial neural network, it is not completely interpretable. because it is like a black box. So the next choice is choosing a learning algorithm, because we have to find best version of the representation, or we have to find a best hypothesis for the given experience. So the example algorithm strategies could be find a hypothesis that minimizes the error. Error is the difference between the output given by the hypothesis and the actual values. There we will be using a famous algorithm called a gradient descent algorithm. Or we can also use the maximum likelihood, where we will be estimating the probability. Or we can also use some evolutionary algorithms or constraint satisfaction algorithms. So each representation has its own algorithms. Like for a neural network, we have a backpropagation. And for regression problem, for linear regression, we have gradient descent. So once we have these choices, we can solve some problems. So let us consider a sample problem of handwritten digit recognition. So why this problem is relevant? So if you take a postcard, where in the typical postcard where we have this pin code, that pin code tells you what is the destination address or the destination post office. If you want to automate the task without manually checking every postcard and finding out where it should be posted, if you have to automate this process, then we should use a system which automatically recognizes these digits. So that is the task. Like it has to take an image and it has to classify image is as 0 to 9. Once we have defined a task, we have to define what is the performance measure. How accurately it will detect the digits from a given image. The percentage of digits that it correctly classifies, that is the performance measure. And what is the data set? Data set of the images which has handwritten digits as well as the labels. And once we have this TPE definition, we can have the choices. The choice of the training experience. It could be the direct, where you have the input and output pairs are available and all the data is available at once. So it is direct and batch. And we have to define, once we have the data, we have to define a target function. We can define it as a formal unknown function, as a function which takes an image and gives output as 0 to 9. Once we have this, we have to consider some representation. So we consider here artificial network, which is suitable for the image data. So these are the sample images, and we will see an implementation with these design choices in the next lecture. So why these design choices are important? Because if we have a wrong choices, we might have an underfitting problem. Suppose if the original relationship is non-linear, if we choose a linear, then we get an underfitting. Similarly, if the model is too complex and if it is simply memorizing, then we get a overfitting. It should be an iterative process. The design choice also, the choice also should be an iterative process. We have to choose one choice and then refine it. In the next lecture, we will be discussing what different perspectives, like what is the statistical or a computing or a psychological perspectives of machine learning, and what are all the different issues in the machine learning.